Okay, everybody, now that we've taken some time doing some algebraic proofs, we're now going to make the scary jump into geometric proofs. So if we take a look at what's going on right here, you'll notice that the proof statement and the givens aren't anything to do with an equation, but rather a geometric figure. And our proof statement in this particular problem right over here is we're going to try to prove that the length of line segment MD, M to D here, is equal to 2 times the measure from M to B. And our given statements here were that M is the midpoint of line segment AB and B is the midpoint of line segment MD. So with those in mind, let's go ahead and get started. So this is what we call a fill-in-the-blank proof. All the statements have been given to us, and we just have to fill in the reasons that go along with them that justify each statement. So our first statement, you'll notice, is identical to the two given statements right up here. So as we said we were going to do earlier, everybody, the first thing we're going to do in just about every proof that we do is state our givens, and that's what's going on right here. So the reason we know those two statements are true is because they were given to us. All right, moving on into the second statement now. We've been told that AM is equal to MB, meaning that the measurement of this segment right here, AM, is equal to the measurement of this segment right next to it, MB. When looking for a reason why that's true, take a look at the givens that we just stated. The first line of the given tells us that M, right here, is the midpoint of line segment AB, and by definition, a midpoint takes a line segment and cuts it up into two smaller pieces that are congruent or that have equal measurements. So the fact that M is our midpoint explains why AM and MB have the same length. And by the same rationale, since B is the midpoint of MD, that explains right here why MB is equal to BD. So, as is often the case, when we are given a vocabulary term within our given, we're going to use that vocabulary term's definition to explain the next step. So B is going to be the definition of a midpoint for us. Now, let's take a look at what's happening right here in step C. And in step C, they're telling us that MD, or the measure of MD from here to here, is equal to the sum of the measurement from MB to BD. And as we look at that, everybody, I see a big segment, MD, equal to the sum of two smaller segments, MB plus BD. So if the concept of big segment equals little plus little sounds familiar, it should, because we did a great deal of that back in the first chapter. And if you remember the name of that, everybody, that is the segment addition postulate. And if you recall, postulates, I believe, were number 4 in that list of things that we said we could use anytime we were trying to explain a reason there. So that explains how we got to C. Now, let's take a look at what happened here to go from C to D. If you look at these two statements here, they're very, very similar. The format is exactly the same. They both begin with an MD equals. They both have an MB plus. And the only difference is that the BD in statement C has been replaced by an MB here in statement D. So they took out one term and they put in something different. Now that should only make sense if those two terms are equal to each other. And sure enough, if we go back up here and we look at what's going on in statement B, we see that MB and BD are equal to each other. And so knowing that, that might explain how they were able to make that substitution right there and eventually replace the BD with an MB right beneath it. So that property right there, hopefully that rings a bell, everybody, is the substitution property of equality. And we can just write substitution, and that'll work fine on that line right there. And the last step then, let's take a look at how they went from D to E. The left side is the same, but the right side has changed from MB plus MB to a 2MB. Now what they really did there is combined like terms. Just like x plus x is equal to 2x, MB plus MB is equal to a 2MB. And while combining like terms is in fact what happened there, that's not one of the 6 things that we get to write down. So what we're going to say instead, everybody, and this is something we just have to get used to, that's substitution also in that 5th step right there. They took out the expression MB plus MB and they replaced it with something equal to it, which was 2MB. So that wraps up that first proof right there within line segments. Let's move on to B. Taking a look at our given statements, they're telling us here that A, B, and C are all collinear points, that the measure of AB right here is equal to the measure of BD. So it might not be a bad idea just to go ahead here and Maybe do some tick marks right here showing that AB and BC are congruent. Gotcha. But they're also telling us right here now that BD and BC are congruent. Well, since BC already has one tick mark, we'll put one tick mark on BD. And now what it looks like, you can tell this easier from the diagram than you can from the text, is that we ended up with three congruent segments right here. And our proof statement right here is that we're trying to prove that B is the midpoint of line segment AC. This is a quick one, everybody. This is only going to take 3 steps. Not very tough at that. All right, so let's take a look at where we're at. So the first statement, A, B, and C are collinear. AB is equal to BD, and BD is equal to BC. You look right up here and notice those are your givens. So our first reason, as is almost always going to be the case in just about every proof we do, is that those statements are given to us. If we take a look at statement B, AB is equal to BC, let's take a look at what's going on here with these steps right above us here, guys. AB is equal to BD, and BD is equal to BC. So if we zoom in just on that, I see 2 equations, but the right side of the first equation and the left side of the second equation are exactly the same. So this is one of the properties that we talked about earlier in the week, everybody, that if 2 quantities, such as AB and BC, are both equal to the same thing, both equal to BD, they've got to be equal to each other. So our reasoning for B, everybody, is going to be the transitive property of equality. If you were thinking substitution would have worked there, you'd have been right about that one also. So this is one that either could be transitive or substitution. Both of those would work. And now that we know from step B here that line segment AB is equal in measure to line segment BC, we're trying to prove that B is the midpoint of AC. Well, given the fact that we've got points that are collinear and the fact that B cuts up AC into 2 smaller line segments that have equal measures, we kind of know that we have a midpoint right there because that's what a midpoint is and that's what a midpoint does. Now, one of the things we said way back on the very first slide of these notes is that definitions are always reversible. And this is a good example of it right here. You'll notice if I go back to example A, that we started off knowing that we had a midpoint that was given to us, and we used the definition of midpoint to say that we had segments that had equal measures. Well, now if we move to this one, we're doing things in reverse. Now that we know we have segments with equal measures, we can now say that B is the midpoint of AC for the same reason there, guys. That, again, is the definition of midpoint. So definitions are reversible. They can go in either order. And that takes care of example B. Easy, right? Yeah, we'll see. All right, on to example C. It's getting a little bit more complex here, but not too bad. All right, we were given that AD, the entire segment here, is equal to 2 times the measure of AB plus the measure of BC. And we're trying to prove now that line segment AB, this little guy right here, is congruent to line segment CD, this one right over here. So let's get rolling. Our first statement here, AD equals 2 times AB plus BC. How do we know that's true? Because that one is given to us. All right, second statement now is where it starts to get interesting. AD, which is the entire line segment, is equal to the sum of the measures of AB plus BC plus CD. Well, if we look at this, AB is the first line segment, BC is the second line segment, and CD is the last one. In a slightly convoluted and inflated way, what they're telling us is big segment is equal to first little segment plus second little segment plus third little segment. And we've seen that one earlier today too, everybody. That is the segment addition postulate. Okay, now's where it gets really interesting. If we take a look at statement C, this is where I tend to lose a lot of people because as soon as the equations get really long and complicated, people tend to check out. But let's try not to freak out. Let's look for similarities between line B and line C. Now, the first thing I notice right here is that if you look to the right of the equal sign here, in both of those 2 equations, I believe we end up with pretty much the exact same expression. Right here in B, I see AB plus BC plus CD, and don't we see the exact same thing here on the right-hand side of statement C? Yeah, they're identical. The difference here, let me switch colors on you now, is that the left side of statement B was AD. The left side of statement C is something totally different, 2AB plus BC. But that sounds a little familiar to me. Right up here in statement A, there's the 2AB plus BC that we were just talking about, and sure enough, it's equal to AD. So what have they done? Going back to statement B, it looks like they took out the AD and replaced it with 2AB plus BC, which right up here in statement A we know is equal to it. So when they take out one complete side of an equation and replace it with something that's equal to it, that's another one right there, guys. That would be the transitive property of equality. But again, substitution would work there as well. So either one of those would be fine, and either one of them would get you full credit. All right, moving on to statement D, let's take a look at what's going on right here. And it looks like there's a lot that's different between C and D. The first thing I notice here is that there's a lot fewer terms in D than we had there in C. So let's take a look at what's missing and see if we can't figure out why and how. I see a CD on the right-hand side of D, and there's a CD as well. There's a BC right here that is now gone. But if you'll notice, there also was a BC on the left side of statement C, and that's gone as well. What else is missing? There was an AB over here, that's gone. And if you notice, there were two ABs on the left side of statement C, but now we're down to just one. So they got rid of one of those ABs. So anytime that identical terms on both sides of an equation magically disappear, that one right there is going to be the subtraction property of equality. You can subtract whatever you want from one side of an equation as long as you do it from both. And this last little thing going on right here, everybody, is a big one, and it's one we want to get used to seeing. So let's take a look at what happened in going from statement D to statement E. They are almost identical. And if you didn't really understand or pay attention to the notations of some things in geometry, you would think that they are. Statement D is saying that the measures of these two segments, AB and CD, are equal to each other. Statement E is saying that the line segments are in fact congruent. So let me put a double tick mark here on AB, and we'll do a double tick mark here on CD. And if that seems obvious to you, if you're sitting here saying, well, yeah, if their measurements are equal, then the segments have to be congruent, you're right. And when you find yourself saying something kind of basic and elemental like that, that is usually a definition. In this case, it's the definition of congruent segments that tells us that if their measures are equal, then the segments themselves have to be congruent. And again, definitions are reversible, so we could do that one in either order. Well, that just didn't look right, so we'll have to fix that. All right, everybody, so there's example C. Let's keep rolling into D. Okay, and in this one right here, we've got this concept of being between here. That's not something we deal with too much, but we'll see if we can plow our way through. And we're trying to prove that AB plus BD, so the first little segment plus the second and third put together, is equal to AC, which is the first two, plus CD, which is the last one. Okay, so how do we know that B is between A and D and C is between A and D also? Because they told us that right up here. So our first reason is going to be given. Okay, now this is a bit of a typo right here, guys. That minus sign that I'm pointing at right here is supposed to be an equal sign. So let me go ahead and make that change right here. That would probably be very confusing if you didn't know that or see that. So that's supposed to be an equals right there. Okay, and let's take a look where we can go with this. AB, which is our first little segment, added to BD, which is the second and third put together, is equal to AD. Very often, but not always, the first time you see an addition statement with an equation in one of your proofs, that is going to be some version of little segment plus little segment equals big segment. That is the segment addition postulate. Okay, let's take a look at C here. Now, C, I see a lot of changes from B, so I'm not sure they're directly related. But once again, I've got AC, which is the first and second little segments put together, plus CD, which is the last one, is equal to AD, which is the whole thing. That is the exact same rationale as what we just used in statement B. So C is going to be the segment addition postulate also. Okay. So now let's take a look at where we're at and where we're going from here. Statement D, AD, and this is now the third time in a row we've seen an AD there, is equal to AC plus CD. So if you look back up above carefully to see where we're at, you'll notice that statement D is exactly the same as statement C, it's just been flipped around. The AD was on the right, now it's on the left. The AC plus CD was on the left, now it's on the right. And we learned the name of a property earlier that says you can flip around the order of an equation. That is the symmetric property of equality, everybody. So we'll go POE for that one as well. And we're just about done. Taking a look at how they got from D to E, once again, look for similarities. The right side of statement D, which is AC plus CD, and the right side of statement E are exactly the same. So there's no change right there. What's different? They got rid of an AD over here on the left-hand side, and they've replaced it with a completely different expression of AB plus BD. So I'm looking up above in my proof for any kind of connection between the AD and the AB plus BD, and I see it right here in statement B, everybody, that AD is equal to AB plus BD. They've taken out the AD and they've made it equal to something, AB plus BD, and replaced it with something that it's equal to. And once again, everybody, what we have right here are two different quantities, AB plus BD and AC plus CD, that were both equal to AD, therefore they must be equal to each other. And that, everybody, is the transitive property of equality yet again. And once more, substitution could work just as well there. I really had to think about how to spell substitution there, and I think we're good. All right. All right, this last one for E, I think we're going to hold off on for now, and I think I'll come back to that one and do that with you on Monday. All right, everybody, have a great weekend.